Scientists have found a huge black hole that formed only 400 million years after the Big Bang, way earlier than anyone thought possible. It's a discovery that changes what we know about the universe's beginning. How did it happen? Join us as we uncover the mystery that could change how we see the universe forever. This discovery is not just a statistical anomaly, it's a paradigm shift. Black holes of this magnitude were not supposed to exist in the early universe, at least not according to prevailing theories. The detection of such massive entities so soon after the Big Bang hints at mechanisms we've yet to understand. It's almost as if the cosmic clock had been set to fast forward in certain regions, producing these immense structures far ahead of schedule. But what could have warped the universe's timeline so drastically? Here's where things get wild. This black hole is a featherweight compared to some of the colossal monsters out there. But its mere existence so early in the universe's timeline throws a wrench into every neat theory about how these cosmic titans grow. If it's not following the rules, what else is out there, breaking the cosmic playbook? Thanks to the James Webb Space Telescope, scientists are diving into a treasure trove of data that's revealing secrets layer by layer, like peeling the universe's ultimate onion. This telescope has spotted galaxies teeming with stars being born, and evidence hints at galactic mergers fueling these baby black holes. It's like the universe's earliest block party, where everyone's smashing into each other and creating new wonders. The potential mechanisms driving the formation of these early black holes are both fascinating and mysterious. One theory suggests that direct collapse black holes, formed from the collapse of massive gas clouds without the intermediate step of star formation, might be the culprits. Another possibility involves hyper-efficient accretion, where smaller seed black holes rapidly devour surrounding matter, growing at unprecedented rates. Either way, the findings push the boundaries of current astrophysical models, and the surprises don't stop there. Alongside CS1019, the telescope uncovered two more rogue black holes in galaxies called CS2782 and CS746. These guys popped up about 1 billion years after the Big Bang, weighing around 10 million solar masses each. They're not alone. They're part of a bigger family of 11 galaxies that formed just a few 100 million years post-Big Bang. This isn't just a history lesson, it's a revolution. The findings are rewriting the manual on how galaxies and black holes buddy up in the universe's early days. Every piece of data is like a puzzle piece in the grand picture of cosmic evolution. Scientists are no longer just theorizing, they're witnessing the universe's chaotic teenage years in stunning detail. Let's dig deeper into what makes this discovery monumental. The spectral data collected on CS1019 unveiled layers of activity, a galaxy bursting with new star formations and hints of a possible galactic merger. Imagine two galaxies colliding, their combined chaos fueling a hungry black hole. It's a dramatic, high-energy scene that might explain how such a massive object could emerge so quickly after the Big Bang. Each collision, each burst of star-making activity adds a new clue to the puzzle of cosmic evolution. Beyond the groundbreaking revelations about CS1019, the discoveries in CS2782 and CS746 further complicate the story. These galaxies, forming roughly 1 billion years after the Big Bang, also host lightweight black holes. While not as young as CS1019, their relatively modest masses challenge assumptions about the speed and methods of black hole growth. Are these objects the remnants of smaller, primordial black holes? Or are they anomalies that point to a previously unknown growth mechanism? The answers might lie in the intricate interplay of stars, gas and gravitational forces within these galaxies. The telescope's survey of 11 early galaxies is a treasure map to understanding the universe's infancy. These celestial artifacts, formed between 470 and 675 million years after the Big Bang, are more than just relics. They're living records of cosmic history. Each galaxy's unique properties, from its star formation rate to the activity of its central black hole, provides critical data for piecing together the narrative of the early universe. One of the most striking aspects of these discoveries is how they challenge long-held assumptions about the early universe. For decades, scientists believed that black holes of such significant mass couldn't form so quickly. Yet here we are, faced with evidence that these objects not only existed, but thrived in the chaotic environment of the early cosmos. This realization forces a re-evaluation of theoretical models, pushing the boundaries of our understanding. The data collected isn't just a goldmine for understanding black holes, it's also shedding light on the broader story of galaxy formation. The 11 galaxies in the CS survey are snapshots of a universe in transition, moving from its chaotic infancy to a more structured adolescence. These galaxies' properties, from their star-making capabilities to their interactions with neighboring systems, offer invaluable insights into the processes that shape the cosmos as we know it. How did the universe grow so fast in its early chaos? The discovery of these black holes and their host galaxies highlights the intricate interplay of physics on cosmic scales. It's not just about black holes devouring matter or galaxies colliding. It's about the dance of gravity, radiation and matter shaping the universe's architecture. From the distribution of dark matter to the influence of cosmic filaments, every factor contributes to the story unfolding before the telescope's unblinking gaze. As scientists delve deeper into the findings, the implications for our understanding of the universe's evolution become increasingly profound. The discoveries about CS 1019 and its counterparts are just the tip of the iceberg. Each new observation, each new piece of data brings us closer to a comprehensive understanding of how the universe's earliest structures formed and interacted. The telescope's mission is far from over. With its unparalleled ability to peer into the distant past, this technological marvel will continue to uncover the secrets of the cosmos. From ancient black holes to the first galaxies, it is more than a tool for observation. It's a gateway to the unknown. The universe's story is far from finished, and with this technology leading the way, we're poised to uncover chapters we never knew existed. As we stand at the forefront of this astronomical revolution, it's clear that this telescope has not just advanced our understanding of the cosmos, it has redefined our place within it. With every new discovery, the telescope reminds us of the boundless wonders waiting to be explored, urging humanity to look beyond and embrace the infinite possibilities of the universe. Chaos and darkness ruled the cosmos, like a wild party before the cleanup crew arrived. Scientists call this messy era the Dark Ages, and for ages it's been like a locked diary, mysterious and frustratingly out of reach. But along comes this cosmic detective with the fanciest gadgets. With its ability to see infrared light, the telescope has blasted open that diary, giving us the juiciest details about how the universe's story began. Spoiler alert, it's rewriting everything we thought we knew. Those cosmic vacuum cleaners that gobble up everything nearby. Its latest jaw-dropper, a black hole so ancient, it formed when the universe was barely 400 million years old. To put it in perspective, if the universe's life were a day, this black hole would show up at 6 a.m. That's ridiculously early, like showing up to a party before the host has even finished setting up. What's more, this black hole is massive. Think millions of times heavier than our sun. How did it get so big, so fast? Nobody's entirely sure, but theories are already crumbling like a poorly stacked Jenga tower. And it's not just the black holes making headlines. The telescope has found galaxies from the universe's toddler years that are stuffed with carbon. You know, the element that's the backbone of life as we know it. Astronomers used to think these kinds of heavy elements took billions of years to cook up in the cores of stars. Turns out, the cosmos was whipping up carbon much faster than anyone imagined. We're talking about stars, the first generation of them, burning bright and exploding in dramatic supernovae, sprinkling the universe with the building blocks of everything from planets to pizza. Then there's the galaxy GSZ 12. Sounds like a sci-fi movie title, but it's actually one of the most fascinating discoveries to date. This galaxy, just 350 million years post-Big Bang, has left scientists scratching their heads. Its chemical signature screams efficiency, like a bakery churning out loaves of cosmic elements faster than anyone thought possible. How were these early stars and galaxies so good at spreading their stardust so far and wide? The data hasn't handed us the answers yet, but it's like a trail of breadcrumbs leading us closer to the truth. The telescope has also found complex organic molecules in galaxies over 12 billion years old. These molecules are cousins of the soot that forms when you burn stuff on Earth. They're not exactly life, more like the ingredients for the soup that could one day become life. Seeing these molecules in such ancient galaxies suggests that the cosmos was gearing up for biological possibilities way earlier than anyone gave it credit for. If you're wondering whether we're alone in the universe, this discovery just tilted the odds in favor of probably not. But let's not forget the heavy lifting the telescope is doing with interstellar gas and dust. It's like a cosmic census, measuring the temperature, density, and composition of stuff in galaxies from over 13 billion years ago. The results are wild. These ancient galaxies weren't lazy little blobs just starting to figure things out. They were bustling hubs of activity, forming stars and elements at breakneck speed. It's like discovering that a preschooler is already acing college-level chemistry. Here's where things get even juicier. The light from these early stars and galaxies didn't just illuminate the universe, it transformed it. The data shows that this light likely ionized the neutral hydrogen that filled space during the Dark Ages, ending the cosmic blackout and letting light travel freely. This process, called reionization, is like the universe flipping the switch on its own power grid. And it wasn't just stars doing the heavy lifting. Supermassive black holes, with their intense radiation, probably played a key role in this transformation. Speaking of black holes, the findings suggest that these cosmic beasts weren't just passive bystanders in the universe's early days. They were more like unruly influences, shaping their surroundings with powerful winds and jets of energy. These interactions may have kick-started star formation and scattered elements far and wide. Were black holes the engines driving galactic evolution? Or were they just side effects of a universe going through rapid growth spurts? The jury's still out, but the telescope is gathering evidence faster than a tabloid chasing a celebrity scandal. Every spectrum the telescope captures is like a postcard from the past, telling us how the universe's first stars, galaxies, and elements came to be. It's not just about understanding where we came from, it's about realizing how interconnected everything is. The same carbon atoms spotted in ancient galaxies are the ones in your DNA, your coffee, and your car's exhaust. The universe isn't just out there, it's in us too. Early clues show the universe was ready for life much sooner than we thought. The discoveries aren't just scientific milestones, they're reshaping our sense of wonder. The telescope's successes have inspired a new wave of stargazers, dreamers, and future scientists. Every image and data point reminds us that we're part of a story that started billions of years ago in a chaotic, star-speckled corner of the cosmos. And as it keeps peering deeper into the universe's past, we're not just learning about ancient galaxies or black holes, we're learning about ourselves. To fully capture the breadth of these discoveries and the resulting questions, let's dive deeper into some of the technical and theoretical implications of these findings. The detection of carbon and other heavy elements at such an early epoch in the universe's history suggests a level of efficiency in the first generation of stars that was previously unimaginable. These population 3 stars, as they're called, are theorized to have been massive and short-lived. Their supernovae would have been incredibly powerful, distributing their nucleosynthetic products into the surrounding interstellar medium. This process kick-started a cycle of chemical enrichment that allowed subsequent generations of stars to form with a richer array of elements. The data is providing the first observational evidence to support this theory, yet it's also raising new questions. For example, how did these early stars form in the first place, given the lack of metals that facilitate star formation in later epochs? Additionally, the presence of complex organic molecules in galaxies that existed less than 2 billion years after the Big Bang is a groundbreaking revelation. These molecules, which are considered precursors to life, indicate that the chemistry necessary for life was already taking place at a time when the universe was still in its adolescence. This challenges the notion that the development of life-friendly conditions is a slow and arduous process. Instead, it suggests that the universe may have been primed for life far earlier than we assumed. The implications for astrobiology are enormous. If the building blocks of life were already forming in distant galaxies billions of years ago, it increases the likelihood that life could have emerged independently in multiple locations across the cosmos. One of the most intriguing aspects of these findings is the apparent discrepancy between observations and existing cosmological models. Before this telescope, simulations of the early universe predicted that the first galaxies would be relatively small and diffuse, gradually coalescing into larger structures over time. However, the telescope has shown that massive and chemically complex galaxies existed within the first few 100 million years after the Big Bang. This challenges our understanding of how galaxies form and evolve, suggesting that the processes driving their growth and chemical enrichment were far more efficient than previously thought. The observations have also shed light on the role of black holes in the early universe. These enigmatic objects, which are typically associated with destruction, appear to have played a surprisingly constructive role in shaping their surroundings. By emitting powerful radiation and ejecting material at high speeds, black holes may have influenced the formation of stars and the distribution of elements within their host galaxies. This raises intriguing questions about the interplay between black holes and their environments. Were they primarily agents of destruction, or did their energetic output help to create the conditions necessary for galaxy formation and growth? Another key area of research enabled by the telescope is the study of reionization, the process that ended the Dark Ages and allowed light to travel freely through the universe. By observing the light from early galaxies and quasars, astronomers are piecing together a timeline of this critical period in cosmic history. The data suggests that reionization was not a uniform process, but rather occurred in a patchwork fashion, with different regions of the universe becoming ionized at different times. Understanding the sources of the radiation responsible for reionization, whether it was primarily stars, black holes, or a combination of both, is one of the central challenges in modern cosmology. As the telescope continues to gather data, it's clear that its impact on our understanding of the universe will only grow. Each new discovery not only answers long-standing questions, but also opens up new avenues of inquiry. Its unprecedented sensitivity and resolution are allowing astronomers to explore the cosmos in ways that were previously unimaginable. Whether it's uncovering the secrets of the first stars and galaxies, shedding light on the origins of complex organic molecules, or probing the interplay between black holes and their host galaxies, the telescope is transforming our understanding of the universe's earliest epochs. These findings will continue to inspire and challenge scientists, pushing the boundaries of what we know about the cosmos. The discoveries are a testament to the power of human ingenuity and curiosity, reminding us that the universe's story is far from complete. As we look to the future, the insights gained from these observations will undoubtedly shape our understanding of the universe and our place within it for generations to come. And there is still more potential to uncover. The discoveries already made suggest that even the most ambitious questions about the universe's infancy might be within reach. For instance, as the telescope peers even deeper, it could potentially reveal direct evidence of population 3 stars, confirming theories about their massive size and short lifespans. Similarly, by studying the dynamics of ancient galaxies, it may shed light on the mysterious processes that led to the rapid formation of supermassive black holes. The ability to study the faintest, most distant objects in the cosmos opens the door to insights about dark matter and dark energy. These enigmatic forces, which dominate the universe, remain poorly understood. By mapping the distribution of galaxies and their movements over cosmic time, the telescope could provide new clues about the nature of these unseen components of the universe. Are we ready to redefine the rules of the universe, or will these discoveries remain unsolved enigmas? Leave your opinion in the comments. Don't forget to like and subscribe for more.